I've noticed that many of the students who come into my class have some rather profound misunderstandings about gravity. I think that the most common misconception the students have is that somehow, if I were to take you and lift you up above Earth's atmosphere, and let's just have Earth's atmosphere in, say, in this region here, if I lift you into space, somehow gravity is negated, that now there's no gravity because you're up in space, and nothing could be further from the truth. If I took you up this high, you would not float. You would not orbit the Earth just because I took you up there. In fact, if I pulled you up from the Earth's surface up to here, far above the atmosphere, and let you go, you would simply fall back down to Earth, straight towards the center of the Earth, because really, gravitation, it turns out, is a force that attracts your center of mass towards the Earth's center of mass. And actually, it's not just you and the Earth that's involved, but it turns out other objects as well. For instance, well, let's consider this. It's not just you being pulled towards the Earth. Newton's third law tells us that the force of attraction, any force at all, is exerted in both directions. Just as the Earth pulls you towards its center, you pull the Earth towards your center. The difference is the Earth's mass is proportionally much larger than you, so because of Newton's second law, it accelerates that much slower. Now let's just put you back down to Earth so you don't sit there hanging in space getting the wrong idea. Now gravity is not just a force that acts between you and the Earth and you. It also exists between the Moon and the Earth. The Earth pulls down on the Moon and the Moon pulls up on the Earth, making tides, by the way. And similarly, if I put you on the Moon, there would be a force of attraction between you and the Moon. If I took you away from both the Earth and the Moon and just put you in space with, oh, I don't know, a bowling ball, it turns out that you and the bowling ball would fall towards each other because the force of gravity actually is a force that exists between any two objects in the universe. This is something that Isaac Newton figured out after much thought. One reason you may not have noticed that you are attracted gravitationally to the bowling balls nearby you, or to your chair, or your pencil, or anything else like that, is because the force of gravity is directly proportional to the two masses involved. It's a force of attraction between two masses, and is directly proportional to the product of their masses. So in other words, the force of gravity depends on the mass of object 1 times the mass of object 2. If either of these masses gets larger, then the force of gravity gets larger. If either mass gets smaller, the force of gravity gets smaller. So let's just say that somehow we were able to take this lovely planet of ours and we were able to make it have a mass that was 2 times greater. What would happen is, let's just say before we did that, you weighed 200 pounds before we did that. After we doubled the mass of the world, you would now weigh instead, you guessed it, instead of 200 pounds, you would weigh 400 pounds. Instead of doubling the mass of the world, we could double the mass of you by having you eat lots of pizza and ice cream. And if your mass doubled, remember, M1 times M2, it doesn't have to be the mass of the world that we double. It could be the mass of you that we double. And if we double your mass, you have twice as many atoms. Well, by golly, you've gone from 200 pounds to 400 pounds. Time to join America's Greatest Loser. Of course, if you went on a diet and you took your mass and reduced it in half, then what would happen is you would go from having a weight of 200 pounds to a weight of only 100 pounds, because if you have half as much mass, you have half as much weight. But if you were more industrious and didn't really want to go on a diet, what you could do instead is you could reduce the mass of the world by half. If you did that, again, the force of gravity would be reduced. So in other words, if you somehow made it so the world had only half as much mass as it had originally, then you would be pulled half as much and you would weigh 100 pounds. Which would be kind of fun because you would only accelerate at 5 meters per second instead of 10 meters per second, and it could lead to a lot of interesting things, but we'd probably lose our atmosphere and suffocate, so it's probably a bad idea now that I think about it. Well, it occurred to old Isaac Newton that you could think of the Earth not as a single object, but as a whole bunch of little tiny objects. So let's just say there's a little bit of rock over here. Well, wouldn't that mean then that there was a force of gravitation between you and that rock and you're pulled that way? It's almost as though there's a little gravitational rubber band pulling you in that direction. But there's also a little piece of world over here, so similarly, you're going to be pulled in that direction as well. And while we're at it, let's consider there's a little piece of world over here and a little piece of world over here, and you're going to be pulled towards both of those as well, like this and like this. And again, think of these like little rubber bands that are going to pull you towards the Earth. Let's just have a couple more of them. There's one of them over here, and there's one of them over here, and let's just connect you with little gravitational rubber bands. One there, and one there. So I want you to think, what would happen if we took you and we lifted you up and let go of you, and we stretched all these rubber bands? What would happen is you would fall straight towards the center of the Earth. So what Isaac Newton realized was that that is why the force of gravitation pulls your center of mass towards another object's center of mass. Usually, in the case of most of us, that other object is the Earth. But it's not really the Earth's center that's pulling on us, but rather all the little parts that make up the Earth. And when he considered this, it led him to a rather interesting thought. Let's just say that I weigh 200 pounds at the surface of the Earth. Sorry to use pounds, maybe I ought to be using newtons. What the heck, let's change it. I weigh 800 newtons. That's better. Okay, that's what I weigh, and I weigh that because all these little pieces of the Earth are all pulling on me, and all of my little pieces are pulling on those, and the sum total of that force is 800 newtons. Well, what would happen, he wondered, if I was to somehow build a special compartment, let's say, like an elevator shaft maybe, and I could get on the special Newtonian elevator, and what this elevator would let me do is it would let me move, and I go, oh, I'm going to disappear. Hang on a second. I want to put you here. Now, I'm going to make a little X. No, I'm not going to make a little X that way. I'm going to make a little X this way. Here's a little X representing the center of the Earth, more or less. So what I'm going to do is I'm going to take you and I'm going to put you in this special air-conditioned elevator that's halfway between the Earth's surface and the Earth's center. Well, what he realized is, remember, think about those gravitational rubber bands. Every little piece of the world is pulling on you. Now, at this point, there's less Earth pulling you down than there was before, and there's actually some Earth pulling up on you. So what would happen is, you wouldn't weigh 800 newtons. You'd weigh somewhat less. Let's just make you weigh 400 newtons. And the reason you weigh less is because you have less world pulling down on you, and you have some world pulling up on you. But wait, there's more. Now what we want to do is take this elevator that you're on and move it so that is at the center of the world, and so are you. Now what we find is that all of the world is pulling you in different directions. Half the world is pulling this way, up on your head. Half the world is pulling you towards your feet. Half the world is pulling you to your right hand. Half the world is pulling you towards your left hand. You're being pulled equally in every imaginable direction. And I think you can see what that means. All the forces would cancel, and you wouldn't weigh the 800 newtons you weighed at the surface or the 400 newtons you weighed part way down. You would weigh 0 newtons. You would be floating inside this elevator. And although it'd be kind of toasty warm, it would be very cool. Well, it turns out the force of gravity is not just proportional to m1, m2, which it is. It's also inversely proportional to the square of the distances between the center of object 1 and the center of object 2. If we change that distance, we're going to make gravity different. So let's just see what that entails. Okay, so you weigh 800 newtons, standing as you are with your center of mass 1 Earth radius away from its center of mass. Now what we're going to do is we're going to take you and we're going to lift you up so the distance between your center of mass and the Earth's center of mass has been doubled. So remember, when we change the distance, the relationship is the force of gravity is going to go down. It's an inverse relationship. Gravity is going to be weaker as you move away from it, and it doesn't get 2 times weaker when you're 2 times farther away. Remember, it's a distance squared function. So at that, don't forget the squaring part. So what that means is you are now, your center of mass is now not just 1 Earth radius away, but instead it is 2 Earth radii away. So what's happened is your distance is twice as far, so instead of weighing half as much, your force of gravity would be reduced to 1/4 of what it was. So instead of being 800 newtons at this distance, you would have a force of gravity of 200 newtons. Well, let's just go ahead and move this stuff out of the way here and move you even farther. Okay, now what we're going to do is we're going to take you and we're going to lift you to your 3 Earth radii. Now let's go ahead and make it 4 Earth radii away. Now what happens is, at this point here, you are, instead of 1, 2, 3, you're 4 times farther away from the center of the Earth than you were to begin with, so the force of gravity is going to be 1 over d squared, and since the distance is changed by a factor of 4, that's 1 over 4 squared. That's 1/16 of what you were before. So I have to take your original weight and divide it by 16, which means you are going to be pulled with 50 newtons of force rather than 800. So the thing to keep in mind is that the strength of gravity depends on just 2 things. It depends on the amount of mass involved, and that relationship is m1 times m2. If you double either of these values, you double the force of gravity. Cut either of them in half, you cut the force of gravity in half. But the force of gravity also is inversely proportional to the square of the distance between the 2 objects' centers. So in that case, if I double the distance, I square that and I end up with 1/4 as much gravitational attraction. If I triple this, I have 3 squared is 9, I end up with 1/9 as much.